So in this video, we're going to talk about the second fundamental issues of a trivially designed page table, which is the page tables are too big, or in other words, the page table is too memory consuming. Recall that in the previous lecture, we've discussed the very first fundamental issue of a trivially designed page table, which is the page tables are just too slow, or the page tables accessing page table incurs like significant runtime performance overhead. Why is that? It's because the page table is an in-memory data structure. It's something residing within memory. So for each and every virtual address translation, you have to get all the way down to the physical memory to just fetch the corresponding page table entry so as to support the virtual page number to physical frame number translation. And this memory access is tedious. This memory access is something that is not needed, which could be eliminated largely because it shows some repetitive, repeated pattern and is not necessary and just inevitably incurs too much performance overhead because a memory access is something that is significantly slower than accessing some special purpose hardware cache, for example, CPU cache. So that is why we introduce TLB to the rescue. The TLB is a hardware cache, which is a translation look-aside buffer, which is a part of the CPU, memory management unit on the CPU chip, okay? So it's essentially a hardware cache, which is solely used for caching the virtual page number to physical frame number translation. So you can think of a TLB as some, hardware cache in front of the page table that is residing within memory. It's a page table cache, okay? So the page table access, this access pattern is repetitive and has certain, cacheable property. So all these different characteristics make the use of introduction of a TLB ideal for serving this page table access patterns. So that was something that we've discussed in our previous lecture. So in this video, we're going to look into the second issue of a typical page table, which is a page table is too memory consuming. It incurs too much memory overhead. Why is that? So let's first take a look at this example. In this example, you're asked to calculate the memory consumption of a typical linear array-based page table, okay? Or how much memory capacity it occupies. In this case, we're essentially looking at a linear array-based page table targeting 32 bits virtual address space. So that translated into how much memory? 2 to the power of 32 bytes, this much memory, right? Okay, and also assume within this virtual address space, the size of the virtual page is 4 KB. So that means the offset fuse has how many bits? Has 2 to the power, has 12 bits, right? Because the size of the page is 4 KB, which is 2 to the power of 12 bytes. So that means the offset has 12 bits. So how many pages in this virtual address space? It has 2 to the power of 20 bytes. So you could just calculate this by using the equation 2 to the power of 32 minus 12 gives you 2 to the power of 20, these many number of virtual pages in this system. Okay, so you are asked to calculate the memory consumption for this particular page table data structure. So in this case, this particular page table consumes a total amount of 4 megabytes, 4 MB memory, assuming each page table entry is of 4 bytes. So how did we get to this number is by using the following equation. So basically, you can understand this as some, the page table that we're looking at has exactly the same number of page table entry, which is the same as the number of virtual pages within this virtual memory system with this virtual address field. So given that this virtual address space has 2 to the power of 20, this many number of pages, okay? So that means you need to have 2 to the power of 20, this many page table entries within this page table data structure, okay? And then 2 to the power of 20 times 4 gives you 4 megabytes. To better understand what exactly this equation means. So first of all, this log 4 KB, this is what? This is the total number of low bits, which is the offset, right? So 32 minus offset gives you what? Gives you the virtual page number bits, okay? So this is bits. Okay, 2 to the power of this, however many bits preserved for a virtual page number field times 4. What is this for? This 4 is the size of the page table entry. Okay, so times this gives you 4 megabytes. So this is the memory consumption for this page table. Okay. Okay, as you can see, so if you just only maintain one single process within this operating system, well, this page table requires exactly 4 MB in terms of memory. But think about this, if you want to maintain like hundreds of different processes, and recall that each process gets its own page table, in memory data structure page table. Okay, so let's assume a system with 100 different processes. We end up spending, 400 MB just solely used for storing this page address translation facility data structure, right? Which is such a wastage of the precious main memory, right? It's too memory consuming, it's too memory intensive. So how to solve this? How to make it more memory efficient, right? What's the solution for this? So there are some seemingly naive solutions. Why not just reduce the granularity, or in other words, increase the page size, right? Why not do this? So why not, just increase the size from 2 KB or 4 KB page into, why not using 4 MB by increasing the size of the page by, let's say, 1,000 times. Why is bad? It's because this relatively coarse-grained paging system has this so-called internal fragmentation issue. And recall that we first talked about this fundamental difference between external fragmentation and internal fragmentation. In this case, in this video, let's first review what exactly the difference between internal and external fragmentation, okay? So in this slide, on the left-hand side, it shows what is so-called external fragmentation. So we have, in this case, within this physical memory address space, we have exactly 4 different processes, P1, P2, P3, and P4. And assuming within each process, its memory space is contiguous. So what's left? This gray area, they are essentially like freely available memory holes, memory space, which are called memory holes. So let's assume, so these are essentially external fragmentation. So assume at a later point of time, there's incoming like large memory allocation request, the size of which is larger than, unfortunately, larger than the size of any of these freely available memory holes. So even though collectively, the aggregated the aggregated free memory capacity is larger than and large enough to accommodate this newly incoming large memory allocation request. But it turns out, if you talk about each and every individual memory host, they are just not large enough to accommodate the new memory request. So these are the fundamental issues. When process comes in and go, they leave the whole physical memory space external fragmented. So if you take a look at the example on the right-hand side, we're looking at what is called internal fragmentation. So internal fragmentation is something that is happening within a single page, no matter whether the page is coarse-grained or fine-grained. But generally speaking, the trend is if the page tends to be more coarse-grained, its internal fragmentation tends to be more severe. If you take a look at this example, this is an example of an allocated 4 MB huge page, let's say for process number 4. So it's highly likely that even though you allocate these pages for a particular process, the process won't be able to fully utilize each and every byte within this allocated 4 MB huge page. So there is always some internal memory fragments which are just really hard, challenging to be fully utilized. So these free space are called internal fragments. So collectively speaking, so cumulatively, all these internal fragments, if you scan through all the pages, so the aggregated internal fragments, they are significant. The total amount of it is significant. So that leads to dramatic memory wastage, right? So these are the issues of so-called memory fragmentation, which leads to memory wastage. So, okay, so another example, real-world example to help you better understand the difference between external and internal fragmentation. Okay, so on highway, let's say under rush hour, under a traffic jam, so the cars are all packed, crowded. So the little space between different cars, between adjacent cars, these are called external fragmentation, right? So, and most of the cars, they are not high occupancy vehicles, but instead their utilization is low. So the driver is the only one sitting inside of a low occupancy vehicle, right? Whereas the passenger seat and back seats, they are just underutilized. Okay, in this case, those freely available space within each and every car is called internal fragments. Okay, so unlike HOV, high occupancy vehicles, their space is almost fully occupied, but there's only one such lane, which is obviously bad. Okay, so this is just some analogy to help you better understand the fundamental difference between external and internal fragmentation. So, speaking of approaches, so next we're going to go through these 3 advanced solutions. So let's first take a look at the very first approach, approach number 1, which is a linear inverted page table. Let's see how linear inverted page table helps solve this, memory wastage issue for page table design. So what exactly linear inverted page table? So the idea is pretty simple. So for a typical page table, the page table is a per process data structure. That means each process maintains its own page table, which is too memory costly, right? So the core idea of linear inverted page table is to just, instead of maintaining a page table per process, let's just maintain a single globally shared page table data structure for this whole physical memory. So basically, you maintain an image, which is just an index for the whole physical memory space. And each page table entry of such globally shared single page table is associated with a certain process. And also, another important field within each and every page table entry of such page table is the virtual page number to physical frame number translation information, okay, which is a core responsibility of a typical page table. So this slide shows the visualization from the hardware perspective, how a linear inverted globally shared page table, how it works, okay? So first of all, as a very first step, the CPU generates the logical or the virtual address. And also the CPU adds one more step. It concatenates. It takes into consideration this PID field, okay? It further uses a combination of PID together with P, which is what? Which is virtual page number. Virtual page number is P. Okay, so it combines these two fields together as the key to look into and search through this linear inverted globally shared page table until it finds a match. So it finds a field which has this core field, the PID plus a VPN field, exactly the match of the key provided, the key of interest. And then as a result, it calculates, it gets the output, which is what? Which is the index of it, which is the index of this matched element, this matched array element, which is I. And this I is essentially the index of this particular, the interested physical frame, physical page. It further concatenate this I, which is essentially the physical frame number field, concatenate it with the unchanged field, which is offset, okay? To construct the final physical address. And then it uses, as a last step, uses the physical address to look into the physical memory. If you further zoom into the physical memory, how it looks like, this requested physical frame, okay? From the perspective of physical memory, its index. So before that, it has exactly I minus 1. These many physical frames ahead of it. So that means this I is essentially an image of the index of this corresponding physical frame. So this is also why it's called inverted, okay? So the ultimate goal of using a linear inverted page table is to use a linear search to find the index. And this index is essentially the physical frame number. So this is also the reason why this page table design is called inverted. Because the opposite way of designing page table is we use the virtual page number. So if we're talking about a linear array-based page table, okay? So the index part is essentially the virtual page number. And we use a virtual page number to index into this page table and fetch the physical frame number. But in this case, we use PID concatenate with virtual page number to perform a linear search. And the result of the linear search is a matched entry. And the index of this matched entry is what we're interested in. And this index, as a result, is the physical frame number, okay? So this linear inverted page table has pros and cons. So the advantage, obviously, it is extremely memory saving, right? Because instead of maintaining individual page table data structures for each and every process, we don't have to do so. we could just maintain a single globally shared page table as an image, as a shadow index that reflects this whole physical memory address space. So this is its pros, but it also has disadvantages, right? So what are the major disadvantages? Well, because for each and every virtual memory access or virtual memory address translation, you need to perform a linear search. That is typically costly. So basically it incurs like O n, assuming this n is the total number of physical pages in the physical memory, which is pretty time inefficient. So what is a solution for this case, right? So that is why we introduced a second advanced approach, which is a hash inverted page table, which is something built on top of approach number one, okay? So the core idea is also simple. So recall that in the very first approach, we use a linear search for each and every address translation. In this case, let's introducing hashing, and we develop something like a hash table. Because for a typical hash table, each and every search, it just incurs constant time, which is O1, right? So the idea is similar, and we use the corresponding information, the PID plus the virtual page number as the key, and we hash the key and get the hash value. And we use this hash value to look into this inverted page table, and we fetch the corresponding matched entry within this bucket. Okay, it's something like, you know, the classic textbook-based chain hash table. Okay, to further understand how exactly it works, let's take a look at this hardware visualization graph. Okay, so in this case, it uses the let's say PID plus this VPN as the key of this hash function, and it generates the hashed value as the index of this hash table. Okay, and then within each entry of this hash table is essentially a chain, right? Which is essentially a linked list. So you have to scan through all the different nodes within this linked list to find a match. In this case, the VPN field is called P. So just linearly search this. This is not a match. So directly jump to the next field, the next node within this linked list. Okay, this happens to be a match because this field turns out to be P, exactly the same as the interested VPN. So as a result, you fetch the most important information, which is R, which is what? Which is the physical frame number. And then the following steps will be exactly the same. Concatenate physical frame number with the offset. And then construct the physical address, and then use the physical address to fetch the data from within physical memory. Okay, so this is how hash inverted page table works. It is essentially just like a hash table. Okay, next, let's move on to the third approach, which is called multi-level page table. So let's say we want to index into a really extremely large virtual address space, where even though using a globally shared page table is not enough. So how to further save space for storing the page table within memory? So the answer is we could use some hierarchical data structure, which is called a multi-level page table, where the page table, instead of being one single level, a flat data structure, we have like hierarchical levels within a page table. Okay. So the high level idea of a multi-level page table is we break this whole flat single level data structure into multiple levels, into pages. So that also means that this entire page table is paged. Okay, so it has multi-levels, and the very top level, it has the something called the directory. okay? And then this directory has to be fit into a single page. So the size of the directory has to be fit into a single page, okay? So each entry, if it's valid, it further points to some second level pages. The second level pages is essentially a page table segment, which is also paged, which has to be fit in a single, memory page, okay? So we have the second valid field. So all these are second level. This is first level. So this is second level. So second level, we have page 1, page 2. So within page 1 and within page 2, they are essentially storing page table entries. So let's say if the size of the page is 4 KB, and each page table entry is 4 bytes, so that means each page could be used to store 1K, 1000, 1024, these many, page table entries. So that further points to the physical memory. So that is about bottom level. The bottom level is essentially the physical. These are essentially physical memory, assuming we have a 2-level page table. Okay. So for example, x86 operating system, it uses multi-level page table, 2-level page table, and it's a simple technique, is 2-level, which is shown over here. Okay, so this slide just shows exactly the example that I just drew in the previous slide. So we're just gonna skip this. So in its simplest form, let's look at how this 2-level page table works. Okay, so in this example, assume we're talking about 32-bit operating system. Okay, so and the size of the page is 4 KB. Okay, so that means the virtual page number fields, if assuming it's a single level page table, is 20 bits. Okay, and the low bits, the offset, is 12 bits. But in this case, let's assume we want to divide this single level page table into 2 levels. So how to partition this? We could just do this equal partition at the high bits field, the VPN fields, so that we have like 2 10 bits, just like shown in this example. We have 10 bits for the first level page table, and we have another 10 bits for the second level page table. And the first level page table is called the directory. Okay, so this next slide, it shows from the the hardware low-level perspective how this 2-level 32-bit paging architecture works. So over here, we equally partition this 20 bits high bits into 2 10 bits fields. Okay, and we use the first 10 bits as the index to index into this outermost page table, which is called a page table directory. Okay, so the index that we use to index into this array is essentially the first 10 bits. Okay, and then we fetch the corresponding page table entry. The page table entry essentially store the starting address of the second level page table, the page of this corresponding second level page table, okay, which points to somewhere over here. And then to index into this second level page table, the page of this second level page table, we need to use another piece of information, which is what? Which is P2, right? So P2 is another 10 bits. Okay. So we use this to zoom in to index into the second level page table. And then we get the corresponding page table entry within the second level page table. So over here, this page table entry, it essentially stores the physical frame number. Okay, and then we use the physical frame number, concatenate it with the D field. Okay, so that we could look into the physical memory and then fetch the corresponding data. Okay, so this is how exactly this whole address translation step mechanism works under a two-level page table. So the question is, what if we want to support like more than two levels? Because in some case, if we're talking about too much extremely large virtual address space, that exceeds the indexing, the addressing capability that could be provided by a two-level page table. How to support this? So we could just add in one more level. If adding in one more level is not enough, let's just add in two levels. Introduce two extra levels. Okay, so the high level idea is similar. Split the page directory, further split the page directory into fine-grained pieces, into fine-grained page at the page granularity, and use another page directory, the outermost directory, as the very first level. Okay. So it's possible to extend to 3 levels or even 4 levels to be able to be capable enough of indexing into an extremely large virtual address space. Okay. So in this example, if we're looking at a virtual address space of a 42-bit operating system. Okay, in this example, the virtual address has exactly 42 bits. So let's assume the size of the page is again 4 KB, which means the offset has 12 bits. So to support 3-level page table, we could just evenly divide the high bits, the VP and the virtual page number bits, the fields, into 3 equal parts. Okay, so the first 10 bits, it's reserved for the very first level page directory, and the second 10 bits reserved for second level page directory. So how it looks like is at the first level, we have a single page. Okay, so this is basically a page of directory. It has valid field and invalid fields. Only the valid fields, only the valid page table entry gets pointed to the second level directory. So each and every second level segment is an individual memory page. Second dir, and within which it has valid page table entries and invalid. Assume it has only one single valid page table entry. And this further points to the third level page table, the third level, which is essentially the page of page table, okay? So within which it has multiple page table entries. And this page table entry further points to somewhere within the physical memory. Somewhere over here. So this is essentially physical frame. Okay, something like that. So this is how a 3-level page table works. Okay, so in the this is the last slide page. It shows a typical example of how 3-level page table looks like.